Hello viewers, in today's class we are going to study a particular type of differential equation known as Bernoulli's equation. So the Bernoulli's equation is of the type dy over dx plus py is equal to q times y raised to n. Now here p and q are the functions of x alone, right? Are the functions of x alone. Now here we'll discuss the solution or the method how to solve this Bernoulli's equation, right? Now here if n is equal to 1, then this equation becomes dy over dx plus py is equal to qy, and if we further solve it, then we see that it becomes dy over dx qy minus py, and we can write q minus p times y, and this equation now can be written as q minus p times dx, and if we integrate both sides, we see that this equation when n is equal to 1 becomes a variables separable form, right? So the Bernoulli's equation becomes a variable separable form if n is equal to 1. Now if we integrate both sides, we can find the solution of this differential equation. Now but we are interested in finding out or in solving this equation when n is not equal to 1, right? So when n is not equal to 1, what we do, we divide this equation, that is we divide equation 1 throughout by y raised to n, right? So if we divide both sides, we get 1 over y raised to n dy over dx plus py divided by y raised to n, and here we get q, because y raised to n and y raised to n get cancelled, right? So now we substitute y raised to minus n plus 1 is equal to, say, v, right? And if we substitute y raised to minus n plus 1 is equal to v, then we get dv over dx is equal to minus n plus 1 times y raised to minus n dy over dx. So here we have used the chain rule, right? So now dy over dx can be written as, 1 over minus n plus 1 times y raised to minus n dv over dx. Now if we substitute this value here, then we get 1 over minus n plus 1 times y raised to minus n dv over dx plus py is equal to q raised to q times y raised to n. Now this can be written as, if we multiply throughout by minus n plus 1 times y raised to minus n, then we get dv over dx plus py times minus n plus 1 y raised to minus n is equal to q times y raised to n minus n plus 1 y raised to minus n, right? Okay, so now this can be simplified as dv over dx plus p times minus n plus 1, and here we have 1 y raised to 1, so it becomes y raised to minus n plus 1 is equal to q times this term and this term get cancelled, so we have q times minus n plus 1, right? Okay, now this equation can further be written as dv over dx plus p times c minus y raised to minus n plus 1 is v, so we can write p times 1 minus n times v is equal to q times 1 minus n, right? So now this equation, this differential equation becomes a linear differential equation of the type dy over dx plus py is equal to q, right? So here p and q are the functions of x, and for y we have v, right? So we can now solve this differential equation by the method which is used to solve this type of equation, and we'll find the integrating factor of this equation, that is e raised to integral of p dx. Now let us solve this problem. Here we have to solve this differential equation, and if we see that or if we compare this equation with this one, we see that this is a Bernoulli's equation, right? So if we compare equation 2 with equation 1, we see that p is equal to 1 over x and q is equal to 1, and for n we have 2, right? So what we will do, we'll divide equation 2 throughout by y square, right? So if we divide both sides by y square, we get 1 over y square dy over dx plus 1 over xy is equal to 1, right? Now we put 1 over or we can write minus 2 plus 1, right? See, we have substituted minus n plus 1 is equal to v. So here we have n is equal to 2, so we substitute y raised to minus 2 plus 1 is equal to v, which can be written as y raised to minus 1 is equal to v, or v is equal to 1 over y, right? So now we'll find dv over dx. So dv over dx is equal to d by dx of 1 over y, which can be written as d over dx of y raised to minus 1. So this is minus 1 over y square dy over dx, right? So dy over dx can be written as minus y square dv over dx, and for y we can write 1 over v, right? So here we can write minus 1 over v square is times dv over dx. Now if we substitute the value of dy over dx here, then we get 1 over y square can be written as v square, and for dy over dx we can write minus 1 over v square dv over dx, and plus 1 over x, and for 1 over y we can write v, and here we have 1, right? So v square and v square get cancelled. So this equation now becomes minus dv over dx plus 1 over x times v is equal to 1. Now multiplying throughout by negative sign, we can write dv over dx is minus, or we can write minus 1 over x times v is equal to minus 1. Now this equation is a linear differential equation of the type dv over dx plus pv is equal to q, right, where p and q are functions of x, and here the integrating factor is given by e raised to integral of p dx, right? So now we have the integrating factor as e raised to integral. For p we can write minus 1 over x dx, and it can be written as minus log x, right? So here we'll use the fact that e raised to log of f of x is equal to f of x. So e raised to minus log x can be written as e raised to log 1 over x. So this is 1 over x, right? So the integrating factor of this differential equation is given by 1 over x. Now the solution of this equation can be written as v times integrating factor is equal to integral of q times integrating factor dx plus c, right? So the solution of this differential equation can now be written like this. So now substituting the value of the integrating factor, so here we have v times 1 over x, and integral for q we have minus 1 multiplied 1 over x dx plus c. Now this is v over x, and we have minus integral of 1 over x, and the integral of 1 over x is log x, so we can write minus log x plus c, right? Now for c we can write log of some other constant, say c of log k. So this can be written as minus log x plus log k. Now by using the properties of log, this can be written as log k over x, right? So now we have v over x is equal to log of k over x, where k is a constant. Now v can be written as 1 over y. So we have 1 over xy is equal to log of k over x. So this is the required solution of this differential equation. Now let us solve one more problem. Here we have to solve this differential equation: x times dy over dx plus y is equal to x cubed times y raised to 6. Now let us first convert this equation into this form. So dividing both sides by x, we have dy over dx plus y over x is equal to x square y raised to 6. Now if we compare equation 2 with equation 1, we see that p is equal to 1 over x and q is equal to x square, and the value of n is 6, right? Okay, so now what we will do, we'll substitute y raised to minus n plus 1 is equal to v, right? So here n is equal to 6, so we can write y raised to minus 6 plus 1 is equal to v, and this can be written as v is equal to y raised to minus 5, that is equal to 1 over y raised to 5. Clear? Okay, so now we'll differentiate v with respect to x. So dv over dx can now be written as d by dx of y raised to minus 5, and this is minus 5 y raised to minus 6 and dy over dx, right? So dy over dx can now be written as 1 over minus 5 y raised to minus 6 times dv over dx, and we'll now substitute the value of this dy over dx in equation number 2. So we get equation 2. Now it can be written as minus 1 over 5 y raised to minus 6 dv over dx plus y over x, and here we have x square times y raised to 6. Clear? Okay, now if we divide both sides by y raised to 6, here we'll divide this equation throughout by y raised to 6, so we get minus 1 over 5 dv over dx plus 1 over x, or y raised to 5, because this y and this y raised to 1 get cancelled with y raised to 6, and we are left with y raised to 5, and here we have x square, right? So now this equation can be written as minus 1 over 5 dv over dx plus 1 over y raised to 5. 1 over y raised to 5 can be written as v, so we have v over x is equal to x square. Now multiplying throughout by minus 5, we get dv over dx plus minus 5 over x times v is equal to minus 5x square. Now this is a differential, linear differential equation whose integrating factor can now be written as e raised to integral of p dx, and we can write integral for p, we can write minus 5 over x dx, and this can be written as e raised to minus 5 log x, right? So this can further be written as e raised to log of 1 over x raised to 5, and this can be written as 1 over x raised to 5, right? Because this can be written as e raised to log x raised to minus 5. Clear? So now the integrating factor of this linear differential equation is 1 over x raised to 5. Now the solution of this equation can be written as v times integrating factor is equal to integral q times integrating factor dx plus c. Now substituting the value of the integrating factor as 1 over x raised to 5 and the value of q as here we have minus 5x square. For q we have this value, so this is v times 1 over x raised to 5 is equal to integral for q we have minus 5 x square times 1 over x raised to 5 dx plus c, right? So this is v over x raised to 5, and here we have minus 5 1 over x raised to 3 dx plus c. So here x square is cancelled and here we are left with 3, right? So this is v over x raised to 5, and here we have minus 5 integral x raised to minus 3 dx plus c. So now we can write v divided by x raised to 5 minus 5, and this is x raised to minus 2 divided by minus 2 plus c. Now multiplying throughout by x raised to 5, we get v is equal to 5 over 2, minus and minus get cancelled, so we have 5x raised to minus 2 times x raised to 5 plus c times x raised to 5. So for v we can write 1 over y raised to 5, and here we have 5 by 2 times x cube plus cx raised to 5, and multiplying throughout by y raised to 5, we further get 5 by 2 x cube y raised to 5 plus c times x raised to 5 times y raised to 5 is equal to 1, right? So this is the required solution of this differential equation.